Hello everyone, this chapter I'll introduce Flink. After this course, we'll be able to understand technical principles and key features of Flink, and also Flink integration in Fusion Insight HD. First, let's take a look at Flink Overview. With distributed technologies evolving all the time, engineers are trying to push those technologies to their limits. Earlier, people were looking for faster, cheaper ways to process data. This need was satisfied when Hadoop was introduced. Everyone started using Hadoop, started replacing their ETLs with Hadoop-bound ecosystem tools. Now that this need has been satisfied and Hadoop is used in production at so many companies, another need arose to process data in a streaming manner, which gave rise to technologies such as Apache Spark and Flink. Features such as fast processing engines, the ability to scale in no time, and support for machine learning and graph technologies are popularizing these technologies among the developer community. Some of you might have been already using Apache Spark in your day-to-day life and might have been wondering if I have Spark, why I need to use Flink. This question is quite expected and the comparison is natural. Let me try to answer that in brief. The very first thing we need to understand here is Flink is based on the streaming first principle, which means it's real streaming processing engine and it's not a fast processing engine that collects streams as mini batches. Flink considers batch processing as a special case of streaming, whereas it is vice versa in the case of Spark. Flink is full of various features. Flink features stream processing, and it's a top open-source stream processing engine in the industry. Flink is distributed, and the lightweight snapshot mechanism helps in achieving a great degree of fault tolerance. It allows Flink to provide high-throughput performance with guaranteed delivery, and is highly scalable that can expand nodes to more than 1,000. Besides, Flink is designed to achieve high performance and low latency. Unlike other streaming frameworks such as Spark, you don't need to do many manual configurations to get the best performance. Flink's pipeline data processing gives better performance compared to its counterparts. Flink also has some other features like low latency. Exactly once means that all data is processed only once due to the asynchronous snapshot mechanism. And HA means high availability, prevent single point of failure. Besides, Task Manager can be scaled out manually. In actual practice, for example, Flink can be used for internet finance services, or clickstream log processing, or public opinion monitoring that require low latency. Flink is compatible well with Hadoop. To be more specific, it supports Yarn to manage and schedule resources for Flink tasks, and can obtain data from HDFS and HBase. Also, it can use all kinds of formatted input and output of Hadoop. Besides, the mappers and reducers of Hadoop can be supported and used along with Flink operations, and the speed of Hadoop job execution by Flink is much faster. Here shows the comparison between performance of open source Storm and Flink. The data comes from Meituan, which is an online ordering platform. It compares the processing capability of orders within 10 minutes. The blue column represents the throughput of a single thread Storm job, and the orange column represents the throughput of a single thread Flink job. Under identity logic, The throughput of a single-thread Storm job is 87,000 pieces per second, and the throughput of a single-thread Flink job reaches 350,000 pieces per second. When the number of partitions of Kafka data is 1, the throughput of Flink is about 3.2 times that of Storm. When the number of partitions of Kafka data is 8, the throughput of Flink is about 4.6 times that of Storm. It shows that the throughput of Flink is 3 to 5 times that of Storm. Then let's take a look at technical principles and architecture of Flink. Flink architecture consists of various components such as deploy, core processing, APIs, and libraries. Flink has a layered architecture where each component is a part of a specific layer. Each layer is built on top of the others for clear abstraction. Flink is designed to run on local machines in a standalone or young cluster, or on the cloud. Runtime is the Flink's core data processing engine that receives the program through APIs in the form of job graph. Job graph is a simple parallel data flow with a set of tasks that produce and consume data streams. The DataStream and dataset APIs are the interfaces that programmers can use for defining the job. Job graphs are generated by these APIs when the programs are compiled. Once compiled, the dataset API allows the optimizer to generate the optimal execution plan, while DataStream API uses a stream build for efficient execution plans. The optimized job graph is then submitted to the executors according to the deployment model. You can choose a local, remote, or young mode of deployment. If you have a Hadoop cluster already running, it's always better to use a young mode of deployment. The libraries layer provides the functions of different APIs of Flink. CEP is used for complex event processing. Table is used for logical table querying processing. Flink ML is used for machine learning. And Jelly is used for image processing. The basic building blocks of Flink programs are data streams and transformations. Conceptually, a data stream is a flow of data records. Data streams can be considered as an unchangeable collection of duplicate data. And a transformation is an option that takes one or more streams as input and produces one or more output streams as a result. When executed, Flink programs are mapped to string data flows consisting of streams and transformation operators. Each data flow starts with one or more sources and ends in one or more sinks. The data flows resemble arbitrary DAGs. Often there is one-to-one correspondence between the transformations in the programs and the operators in the data flow. Sometimes, however, one transformation may consist of multiple transformation operators. Data source and sink are easy to understand, which could be HDFS files, Kafka, or text. Here distinguish the data sources of Flink for batch processing and stream processing. For batch processing, it supports files in HDFS or local file system, or a text file, a CSV file, and it also supports JDBC, HBase, and maybe collections. As for stream processing, it supports commonly files or Kafka or Flume. Here are some common transformations like map, flat map, filter, keyby, and so on. The data stream transformation process of Flink is similar to that of Spark. From this figure, data in a text file format is read from HDFS into data streams, then performs some operations such as flat map, keyby, and then window operations are performed. Finally, sync the results to HDFS in a text file format. In a Flink application, the following key roles are involved. Flink client is used to submit jobs, or you can say streaming jobs to Flink. Job Manager is a management node of Flink. It manages all task managers and schedules tasks submitted by users to specific task managers. In HA mode, multiple job managers are deployed. Among these job managers, one of which is selected as the leader, and the others are standby. The resource manager in YARN is used for scheduling and allocating the resources for Flink applications. Task Manager here is a service execution node of Flink. It executes specific tasks. A Flink system could have multiple task managers, and these task managers are equivalent to each other. Each task manager is a JVM process and may execute one or more subtasks in separate threads. To control how many tasks a worker accepts, a worker has so-called task slots. Each task slot represents a fixed subset of resources of the task manager. A task manager with 3 slots, for example, will dedicate 1/3 of its managed memory to each slot. Slotting the resources means that a subtask will not compete with subtasks from other jobs for managed memory, but instead has a certain amount of reserved managed memory. Note that no CPU isolation happens here. Currently, slots only separate the managed memory of tasks. By adjusting the number of task slots, users can define how subtasks are isolated from each other. Having 1 slot per task manager means each task group runs in a separate JVM. Having multiple slots means more subtasks share the same JVM. Tasks in the same JVM share TCP connections and heartbeat messages. They may also share data sets and data structures, thus reducing the per-task overhead. Flink supports YARN-based cluster management mode. In this mode, Flink serves as an application of YARN and runs on YARN. This figure shows how Flink interacts with YARN. The Flink YARN client first checks whether the requested resources for starting the YARN cluster are available. If yes, the client uploads the jar package and configuration file to the Hadoop distributed file system. Then, Flink YARN client communicates with the YARN resource manager to request a container for starting the application master. After all node managers of the YARN cluster finish downloading the jar package and configuration file, the application master is started. During application master startup, the application master interacts with the YARN resource manager to request the container for starting task manager. After the container is ready, the task manager process is started. In the Flink YARN cluster, the application master and Flink job manager are running in the same container. The application master informs each task manager of the job manager RPC address. After task managers are started successfully, they register with the job manager. After all task managers successfully complete registration with the job manager, Flink is started in the YARN cluster. Then the Flink YARN client can submit Flink jobs to the job manager, and Flink can perform mapping, scheduling, and computing for jobs. Like I've said earlier, a Flink program consists of two building blocks, stream and transformation. Conceptually, a stream is a flow of data records, and a transformation is an operation that takes one or more streams as input and produces one or more output streams as a result. When a Flink program is executed, it's mapped to a streaming data flow. A streaming data flow consists of a group of streams and transformation operators. Each data flow starts with one or more source operators and ends in one or more sink operators. A data flow resembles a DAG. Applications in Flink can be executed in parallel or distributed modes. A stream can be divided into one or more stream partitions, and an operator can be divided into multiple operator subtasks. The executor of streams and operators are automatically optimized based on the density of upstream and downstream operators. Operators with low density cannot be optimized. Each operator subtask is separately executed in different threads. The number of operator subtasks is the parallelism of that particular operator. The parallelism, which is the total number of partitions of a stream, is that of its producing operator. Different operators of the same program may have different levels of parallelism. Operators with high density can be optimized. Flink chains operator subtasks together into one task. That is an operator chain. Each operator chain is executed by one thread on Task Manager. In the upper part of the preceding figure, the condense source and map operator is chained into an operator chain. That is a larger operator. The operator chain, keyby, and sink all represent an operator respectively and are connected with each other through streams. Each operator corresponds to one task during the running. Namely, there are three tasks in the preceding figure. In the lower part of the preceding figure, each task, except sync, is divided into subtasks, so the parallelism of sync operator is 1. Aggregating events, such as counts, sums, works differently on streams than in batch processing. For example, it's impossible to count all elements in a stream, because streams are in general infinite, which means unbounded. Instead, aggregates on streams are scoped by windows, such as count over the last 5 minutes or sum of the last 100 elements. Windows can be time-driven, for example, every 30 seconds, or data-driven, for example, every 100 elements. One typically distinguishes different types of windows, such as tumbling windows, sliding windows, and session windows. If you would like to know how many vehicles pass that location, you simply sum the individual counts. However, the nature of a sensor stream is that it continuously produces data. Such a stream never ends, and it's not possible to compute a final sum that can be returned. Instead, it's possible to compute rolling sums, return for each input event an updated sum record. This would yield a new stream of partial sums. However, a stream of partial sums might not be what we are looking for, because it constantly updates the count, and even more important, some information such as variation over time is lost. Hence, we might want to rephrase our question and ask for the number of cars that pass the location every minute. This requires us to group the elements of the string into finite sets. each set corresponding to 60 seconds. This operation is called a tumbling window operation. Tumbling windows discretize a stream into non-overlapping windows. For certain applications, it's important that windows are not disjunct, because an application might require smooth aggregates. For example, we can compute every 30 seconds the number of cars passed in the last minute. Such windows are called sliding windows, whose time overlaps. A session window is a window which allows us to group different records from the stream for a specific session. This window will start when the session starts and evaluate it when session is ended. This window also will support checking multiple sessions at the same time. Session windows are often used to analyze user behavior across multiple interactions bounded by session. Apache Flink offers a fault tolerance mechanism to consistently recover the state of data streaming applications. The mechanism ensures that even in the presence of failures, the program state will eventually reflect every record from the data stream exactly once. We call it checkpoint mechanism. The central part of checkpoint mechanism is drawing consistent snapshots of the distributed data stream and operator state. These snapshots act as consistent checkpoints to which the system can fall back in case of a failure. A core element in Flink's distributed snapshotting are the stream barriers. These barriers are injected into the data stream and flow with the records as part of the data stream. Barriers never overtake records. The flow is strictly in line. A barrier separates the records in the data stream into the set of records that goes into the current snapshot and the records that go into the next snapshot. Each barrier carries the ID of the snapshot whose records it pushed in front of it. Barriers do not interrupt the flow of the stream and are hence very lightweight. Multiple barriers from different snapshots can be in the stream at the same time, which means that various snapshots may happen concurrently. This mechanism ensures that even in the presence of failures, the program state will eventually reflect every record from the data stream exactly once. When an application requiring the checkpoint mechanism is started, the job manager of Flink creates a checkpoint coordinator for the application. The checkpoint coordinator is responsible for creating snapshots of the application. Users can set the checkpoint interval by calling the setCheckpointInterval. The checkpoint coordinator periodically sends barriers to all source operators of the data streaming application. When a source operator receives a barrier, it pauses data processing, creates a snapshot of its current status, saves the snapshot to the specified persistent storage, and reports to the checkpoint coordinator that the snapshot has been created. In addition, the source operator broadcasts the barrier to all downstream operators and resumes data processing. As described previously, each operator creates the snapshot and broadcasts the carrier to downstream operators until the barrier is sent to the sync operator. The sync operator also performs the same operations. After the checkpoint coordinator receives the reports from all operators, snapshots of this checkpoint interval are created successfully. Otherwise, the checkpoint coordinator determines that snapshots of this interval fail to be created. Flink also supports multiple source checkpoint mechanism. This page takes the double source checkpoint mechanism as an example. Assume that operator C has two input sources, A and B. In checkpoint interval, operator C receives the barrier sent from source A first for some reasons. Operator C then blocks the input channel of source A and receives data only from source B. When the barrier sent from source B arrives at operator C creates a snapshot of its current status and reports to the checkpoint coordinator that the snapshot is created. Then operator C merges these two barriers into one and broadcasts the barrier to all downstream operators. If a fault occurs, the checkpoint coordinator instructs all operators in the data flow to restore the status of a certain checkpoint interval, and then the operators resume data stream processing. The distributed checkpoint mechanism ensures that data is processed exactly once. Then let's take a look at Flink integration in Fusion Insight HD. In Fusion Insight, Flink is a unified computing framework that supports both batch processing and stream processing. It provides a stream data processing engine that supports data distribution and parallel computing. And in the Fusion Insight Hadoop platform, users can view the running status of Flink tasks by Young Web UI. Besides, Flink interacts with the following components: HDFS, which is for reading and writing data. Young is used to schedule and manage resources for running tasks, and Flink relies on Zookeeper to implement the checkpoint mechanism. In addition, Flink can receive data streams sent from Kafka. So this chapter mainly talks about Flink, like its basic concept, application scenarios, technical architecture, window types, and Flink on Yum. It also introduced Flink integration in Fusion Insight HD. Okay, that's all for Flink. Thank you.